Welcome to this video on the link between temperature and the rate equation. And let's just start off by considering again why temperature affects the rate of a reaction. So pause the video now and test yourself out. Okay, so in the framework of collision theory, temperature effectively is just increasing the kinetic energy of the particles. They're moving faster. That means they're going to collide more often. And actually, the collision frequency will increase as T, essentially the square root of temperature. The collision energy is also going to increase substantially. And actually, it's this that is the most significant factor, the collision energy. So collision energy increases. That means the likelihood of any given collision is much more likely to be successful if the temperature is high. You're much more likely to provide that activation energy that the particles need at higher temperatures. The collision orientation, no effect. So if you're ever asked a question about this, you need to make sure you include the fact that what temperature does, the effect on the collision frequency, the more significant effect on the collision energy, and then finally just a summary that you have more successful collisions per second. Okay, let's think now about the Maxwell-Boltzmann distribution. This is a distribution which shows the energy of the particles and the number of particles with a given energy. It's a frequency distribution. So if we start off at low temperatures, and the distribution is going to look something like that. Remember, it's asymptotic to the energy axis. So this would be low temperature, and then high temperature. Essentially, on average, the particles will have more energy, so the peak of this graph is going to shift to the right, but the area under the curve is going to stay constant, so something like that. This is high T. Okay, now the crucial bit that you need to include on this diagram is where the activation energy is. So you're starting off the particles starting at a ground state of 0. This is the amount of energy you need to include or need to provide in order to get them over the energy barrier. So that's the activation energy. And crucially, this area under the curve represents how many particles will have energy greater than the activation energy. And what you can see is that at higher temperature, you have many more particles with energy greater than the activation energy, and therefore you're more likely to have collisions with energy greater than the activation energy. Okay, now thinking about temperature and the rate equation. So imagine we've just got this reaction happening here. The rate equation for this reaction is going to be K times the concentration of A times the concentration of B, and these are going to be raised to particular powers, their orders. We don't know what those are from the stoichiometry of the equation. Now, if we think about increasing temperature, well, what effect will temperature have? So as temperature increases, well, effectively these concentrations, so the concentrations of the reactants, are constant. Or at least we can arrange them to be if we're working a gas in a solution. The temperature won't affect the concentration. And so, therefore, the only thing that must be affected is the rate constant. So rate constant will be affected. How will it be affected? Well, the rate of reaction increases as temperature increases, so we're going to have to say the rate constant K must increase. Okay, now can we be a bit more precise about the nature of that relationship? Well, it was studied by Swedish chemist Svante Arrhenius back in the late part of the 19th and early 20th century, and he came up with the following relationship that links the rate constant. So he said that the rate constant is linked in the following way. So let's think about what these parameters actually mean. So that is the rate constant we discussed before. Now the factor A is known as a pre-exponential factor because this is an exponential. So this is the pre-exponential. And what the pre-exponential factor is called the information that it contains is sometimes also known as a frequency factor, and that's more helpful, I think, to help us to understand what it's actually doing. It's essentially telling us how frequently these molecules are colliding. Now that's going to be determined partly by concentration, which is why sometimes a frequency factor can be misleading, but effectively it's telling us how often the particles are colliding, and that's going to have all things about the orientation of the particles in as well. Now this second term here in the exponential has got two bits to it. The first bit is the activation energy. This is the activation energy. So it's basically telling us that there is a link between the rate constant and the activation energy, and we'll think more about that in a moment. The next bit it has in it is this term RT, and what this term RT is doing, you've got the temperature in there. Now R is the gas constant, and 8.314 joules per Kelvin per mole is the typical unit that it's quantity that it's given. So this is the gas constant. So if you think about quantity RT, let's just briefly have a look at its units. Well, it's going to be joules per Kelvin per mole multiplied by temperature, and that would be in Kelvin. So the Kelvins would cancel, and we've just got something. RT is something which is in joules per mole. So if I just find a suitable pen that I haven't already used, the black one here. Perhaps no, that's not going to be very clear. Let's try this orange one. So this quantity here, RT, is basically telling us the average energy of the particles. So what this quotient here is doing is it's comparing the activation energy to the average energy of the particles. If the average energy of the particles is high, then this term is going to tend towards 1. If the average energy is very low, this term will tend towards 0. Let's see that in a bit more detail now. So there's the Arrhenius equation. So first thing this is telling us is that there is a link between the size of the rate constant and the activation energy. Now if we think about this on an energy level diagram, what we're basically going to conclude here is that, let's say these are reactants A plus B and C. Now if this reaction has a very high activation energy, so this is activation energy, if the activation energy is high, then we're going to conclude that K will be small. However, if this is slightly different and my activation energy is very small, the EA is small, then assuming temperature is constant and such like, then K will be large. There's this relationship, and it makes sense. If the energy barrier for the reaction is very small, then you'd expect it to be a very fast reaction. If the energy barrier is very large, then you'd expect it to be a very slow reaction. Now finally, let's just think briefly about what the relationship between K and temperature is actually going to look like. So a usual way to do this is to think about some limits. So at low temperature here, so this is absolute temperature, this is temperature in Kelvin. So absolute 0, so this is temperature in Kelvin, so we've got absolute 0 here. So low temperature, well, this quotient is going to have a very, very small denominator. And so this e to the minus EA over RT is going to tend towards e to the, well, if this is going to be a very, very small, it's going to tend to e to the minus infinity. In other words, it's going to tend to 0. And so K is also going to tend to 0. So I can put that point on. So K tends to 0. 0 Kelvin, it's 0. Now let's think about what happens at high temperature. So high temperature here, then this temperature is going to get very, very large. So this denominator is going to be absolutely huge. That means this quotient is going to be very small. So e to the minus EA over RT is going to tend to e to the minus 0, which is essentially tending to 1. And so K is going to be just tending to A times 1, which is just A. So if I just try and sort of summarize that just by showing you the graph, then essentially what we've got is that at high temperature, K is going to asymptote towards a value of A. And so if we show that graphically, what's that actually going to look like? Well, it's going to start off small, and then eventually it's going to become pretty close to being A. And that's why that it's possible to interpret this exponential factor here as a bit like a probability, which just ranges between 0, so e to the minus infinity is 0. So it ranges between 0 and 1, and what that's saying is at low temperature the probability of your collision being successful is 0, or close to 0, and at high temperature the probability is close to 1. And so at high temperature what you get is a rate constant that's basically just the pre-exponential of the frequency factor, essentially how often you're colliding, because every collision results in a successful reaction.